Now, as we discussed that this is the PV and TS diagram of the reversed Brayton cycle, right? And this pressure is P1 is equal to constant and this pressure is, let us say, P2 is equal to constant. Now we have to find what is the COP of this reversed Brayton cycle. We have to derive the expression for it. But you know that the COP of this case will be equal to your refrigeration effect, that is heat supply, divided by your net work done. And net work done will be equal to compressor work minus turbine or expansion work. Right? This we have to derive for this. Now we hope that your thermodynamics basic concept of how to write the equation of steady flow energy equation and what is the change of enthalpy and all. I hope that discussion of the thermodynamics, your concept of the thermodynamics are very good. So we are directly using the equations and directly using the results here. So if the question came in your GATE exam, then the question will be the straightforward question, right? You just put the formula and you will get the answer. But if we are talking about the engineering services exam or some exam in which some conventional questions will ask, then they will give you a more complex situation, or they can give a twist in the question, and if you are not good with the concept, then you can do a mistake, right? Definitely you will do a mistake. So just pay attention here while I am deriving the equation of the COP, and just pay attention that that assumptions we are taking while deriving the expression. So now let us start with the, and we'll take one process one time. First of all, let us write the steady flow energy equation. I hope you all are good with the steady flow energy equation, but for your understanding, let us write the steady flow energy equation once. The steady flow energy equation, we know that this is equal to H1 plus V1 square by 2 plus GZ plus heat added to the system per unit mass is equal to H2 plus V2 square by 2 plus GZ2 plus work done by the control volume, WCV, work done by the control volume. This is a steady flow energy equation, you know this, right? Now let us apply this equation for one process at a time. Let us take process 1 to 2. First of all, let us take process 1 to 2. This process 1 to 2 is your reversible adiabatic compression. I write here reversible adiabatic compression. This is the first process, right? If I apply the steady flow energy equation for this first process, then I can write this equation, I can write again H1 plus V1 square by 2 plus GZ1 plus heat supply is equal to H2 plus V2 square by 2 plus GZ2 plus work done by the control volume, right? Now in this equation, if we see that in this equation the process is your reversible adiabatic, and for the reversible adiabatic process we know that for the adiabatic process this heat transfer is zero. And we are neglecting, this is the first assumption we are writing. I am writing all the assumptions with the red pen so that you will be able to understand what are the assumptions we are taking while deriving these equations, right? These equations cannot be applied in any question. There are some assumptions which we have to take. We are neglecting the changes in kinetic energy and potential energy. This is the first assumption of this equation, that we are neglecting the changes in kinetic energy and potential energy in the compressor. If in the question they are giving the velocities at the inlet and velocity at the outlet, so you cannot neglect the changes in kinetic energy. But here I am neglecting the changes in kinetic energy and potential energy. So this V1 square by 2 minus V2 square by 2 is 0. GZ1 minus GZ2 is 0. So from here I can write this will be equal to H1. H1 is equal to H2 minus WC. Why minus? Because work is done on the system. If this compressor is your system, then we are doing work on the system. So work done on the system will be negative. This will be minus. So from here you can write WC will be equal to H2 minus H1. Now WC is equal to H2 minus H1. The enthalpy at point 2 minus enthalpy at point 1. This formula is applicable. Now just pay attention guys. This formula is applicable with only one assumption, that is neglecting changes in kinetic energy and potential energy 0. To apply this equation, your assumption is, if I write it with blue pen, the assumption of using this equation is only changes in kinetic energy and changes in potential energy is 0. This is the only assumption of using this. Now we know that if we have an ideal gas, if the second assumption I am taking ideal gas, this is the second assumption, that is ideal gas. For ideal gas, you know that, for ideal gas we know that dH will be equal to Cp dt. This is we know. You know from the basic understanding of thermodynamics, I already give you the explanation and all the equations that dH is equal to Cp dt. dH is equal to Cp dt. To use this formula you have two conditions. One is if the process is constant pressure process, any substance, for any gas or any fluid, you can use this formula. If the substance is an ideal gas, if you fix the ideal gas, then for any process you can use this formula. So I am taking here the assumption ideal gas. So for ideal gas I am using dH is equal to Cp dt. Right? We are using dH is equal to Cp dt. So from here you will get that work required by the compressor will be equal to Cp into T2 minus T1. Cp into T2 minus T1. This is per unit mass. Everything is going on per unit mass, right? If you want to find out total, then you have to multiply it with the mass of the refrigerant which is flowing. So this formula, now please pay attention. This formula is only valid for ideal gas. For ideal gas and changes in kinetic energy 0 and changes in potential energy 0. To using this formula, that is work consumed by the compressor which is equal to Cp into T2 minus T1, this formula is only applicable for the ideal gas. If in the question they are not giving you the ideal gas, then you cannot use this formula, that is Cp into T2 minus T1. You have to go with this formula H2 minus H1. And if they are giving some velocity also at the inlet and outlet, then you cannot use this formula. You have to go with the basic of thermodynamics, that is the steady flow energy equation. Right? Now, I hope you understand this concept. This is most important because here is the thing where you will definitely do a mistake if your concepts are not clear. What the students are doing, they are just cram the formula that this is the COP of the Brayton cycle, and when they show the question they just simply use the formula and get the answer. And if you are doing that, then definitely you will make a mistake, your answer will be wrong. And now the students will be very confident that this is a very easy paper, this is a very easy question of RAC. They will directly use the formula and get the solution for the COP of reverse Brayton cycle. But they do not know these concepts, right? where to use which formula, what is the assumption of it. That is the beauty of thermodynamics, and that is the beauty of the GATE paper or RAC. They will give you a tricky question where maybe they will not give an ideal guess, and still if you are using this formula, then you will get a wrong answer, right? So this is the for process 1 to 2. This is for process 1 to 2. So this work required by the compressor will be H2 minus H1, or you can say Cp into T2 minus T1. And for this process also, for this process 1 to 2, we know that this is an reversible adiabatic process. So we can say that for this process, your entropy at point 2 will be equal to entropy at point 1. Because it is an isentropic process, so entropies will be constant. Entropy will be constant. And one more equation which you can write from here, because this is an adiabatic process, then you can use this adiabatic formula, that is your adiabatic formula is PV raised to power gamma is equal to constant. You can use it. So from here what we can use, that T2 by T1 is equal to P2 by P1 raised to power gamma minus 1 upon gamma. Right, this you know. T2 by T1 is equal to P2 by P1 raised to power gamma minus 1 upon gamma. And now if you want to give it one more step ahead, if we want to give it one more clear picture, then if I say that this is gamma C, if I write for compression, you can better write it like gamma C minus 1 upon gamma C, where we can say that gamma C is the adiabatic constant for compression. In GATE they will not give so much detail, but in engineering services you may find that gamma are different for the compression process and for the expansion process. So we'll go with that. Here gamma C minus 1 divided by gamma C, this is T2 by T1. And this P2 by P1 is known as pressure ratio. Pressure ratio means that how much is the pressure increased by the compressor, right? Compressor is increasing the pressure from P1 to P2. So P2 by P1 is known as pressure ratio, and that will be equal to Rp. We denote it with the letter Rp. So Rp is the pressure ratio. So this is for the process 1 to 2. This is all about the process 1 to 2, that how to find the work, what are the basic equations. Entropies are equal. T2 by T1 is equal to P2 by P1 raised to power gamma C minus 1 upon gamma C, and P2 by P1 is known as pressure ratio. Similarly, we will do these things for the different process, for process 2 to 3 and process 3 to 4 and process 4 to 1. So this is for process 1 to 2. Now let us move to the process 2 to 3. If I rub it, now let us move to the process 2 to 3. I hope you write all this right. Process 2 to 3. Process 2 to 3 is, if we write here, process 2 to 3 is reversible isobaric heat rejection process. Heat rejection process. This is the process 2 to 3. So this is the steady flow energy equation, that is H1 plus V1 square by 2 plus GZ1 plus heat transfer or heat added to the system is equal to H2 plus V2 square by 2 plus GZ2 plus work done by the system or work done by the control volume, if you say precisely. Now if I assume, the first assumption is changes in kinetic energy is 0 and changes in potential energy is 0. If we assume this, and you know that this process 2 to 3 and this process 4 to 1, they are doing in the heat exchanger. They are in the heat exchanger. And in the heat exchanger, you may find that in the heat exchanger, we don't want any work from that. So this WCV is 0. This WCV is 0. So this steady flow energy equation will be equal to H1. Q is the heat added to the system, but now heat is going out of the system. So this will be equal to H1 minus QR. What is this? Heat rejected minus QR is equal to H2. Is equal to H2. So from here you can write, note 1. Right, you can write it like this. Okay, if you are having some confusion, this will be H2 plus V2 square by 2 plus GZ2 is equal to H3 plus, okay, if you write like this, V3 square by 2 plus GZ3, right, you can write like this. So this will be equal to H2 minus QR is equal to H3. So from here you can write QR will be equal to H2 minus H3. QR will be equal to H2 minus H3. To use this equation, what is our assumption? That is changes in kinetic energy 0, changes in potential energy 0. Now, pay attention here. This is which process? Constant pressure process. This is constant pressure process. And we know that for a constant pressure process, dH is equal to Cp dt. You can write it for any substance. We know this. For any substance we can write. So without taking the assumption of ideal gas, because this is a constant pressure process, so you can write QR will be equal to Cp into T2 minus T3. This you can write directly without taking the assumption of ideal gas, because this is a constant pressure process. Now this is the most important thing here, that heat equation you can write Cp into T2 minus T3 whether the refrigerant which is flowing in this cycle is an ideal gas or a real gas. It may be anything. You can write this equation. The only assumption of writing this equation is changes in kinetic energy 0, changes in potential energy 0. This you have to remember, right? This is a very, very important thing, that when we can write this QR is equal to Cp into T2 minus T3, right? Now if we talk about for the process 2 to 3, pressure is same, so you can write pressure at point 2 will be equal to pressure at point 3, right? And if you want to write what is the changes in entropy, if you write S2 minus S3, S2 minus S3 will be equal to how much? SPLN. S2 minus S3 will be equal to SPLN T2 by T3, right? This is a finite body, and you know that ds will be equal to CPLN T2 by T1 for a process in which the finite temperatures are discussed about. This is the heat transfer to the finite temperature difference, or finite bodies. Between the finite bodies we are transferring the heat, right? It is not a source or not a sink. So S2 minus S3 will be equal to CPLN T2 by T3. This you know, right? From if you want to write how we can know for a reversible system, what you know, ds is equal to dq by t. You know this, ds is equal to dq by t. So dq is equal to how much? Cp dt. You know that dq is equal to Cp dt. Here if I write this, dq is equal to dh and dq is equal to dh is equal to Cp dt. So dq is equal to Cp dt by t. If you integrate it from T2 to T3, if you integrate it, so you will get S3 minus S2. So I just reversed it, or you can write from S2 to S3. If you want to integrate, then how much you will get here? S3 minus S2 is equal to Cp ln integration of 1 by T ln T3 by T2, right? Or I can write S2 minus S3 like this, right? This equation is the one and the same thing. If you take minus common, so they are both the same. So this is the entropy change for this process 223, right? So you are better understand that why I am using these equations, right? In some of the questions they may ask the entropy change, they may ask something else, so you will be able to better understand that what is going on and how to write the equations. Next we'll talk about the process 324, right? I am rubbing this. Next process is process 324. Why I am writing here? Because we need this diagram for the better understanding in our later discussions. Next process is process 324. Process 324. 324 process is reversible adiabatic expansion. Reversible adiabatic expansion. So for this, what is the for process 324, what is the steady flow energy equation? Steady flow energy equation will be H3 plus V3 square by 2 plus GZ3 plus heat added to the system is equal to H4 plus V4 plus V4 square by 2 plus GZ4 plus work done by the system. Now we know that this is an adiabatic process. So for the adiabatic process, heat transfer is 0. And if I assume the first assumption, that is changes in kinetic energy is 0 and changes in potential energy is 0. We are assuming this as our first assumption, that changes in kinetic energy and potential energy is 0. So from here I will get H3 is equal to H4 plus because here this is the turbine work and turbine is giving some work to you, right? Plus WT or turbine work WT, let us say. So this will be WT will be equal to H3 minus H4. WT will be equal to H3 minus H4. So the assumption of using this equation is only one assumption, that changes in kinetic energy 0 and changes in potential energy 0. Just make one thing clear, that if the velocity values or the height values are giving for the point 3 and point 4, then you cannot use directly H3 minus H4. You have to go with your steady flow energy equation, basic equation, right? This we can use if we neglect that. Now, this is which process? Reversible adiabatic process. So I cannot write dH is equal to Cp dt unless and until we are assuming ideal gas. This is important. If I take the second assumption, that is ideal gas, so for an ideal gas you can write dH will be equal to Cp dt, and if I assume this as an ideal gas, so I can write work done by the turbine will be equal to Cp into T3 minus T4. Cp into T3 minus T4. The assumption of using this equation is, first is this one only, changes in kinetic energy 0, changes in potential energy 0, and second is the ideal gas. This is important thing. Gas must be ideal. If ideal gas is not there, if they are saying some other fluid is flowing, then you cannot use Cp into T3 minus T4. You cannot use this, right? I understand. This is which form? Which? Reversible adiabatic. So S3 will be equal to S4. Entropy must be equal. We know this. And if you see the ratio of the pressure ratios, so I can write for 3 to 4, I can write T3 by T4 will be equal to P3 by P4 raised to power gamma E minus 1 upon gamma E. I am writing gamma E, right? And gamma E is the adiabatic constant. Adiabatic constant for expansion. In engineering services only they can give this gamma E and gamma C as separate, but in GATE they will give only 1.4 only, right? So this will be this one, and you know that what is P3? P3 is equal to P2, this is constant, and P4 is equal to P1. So I can write this is equal to P2 by P1 raised to power gamma E minus 1 upon gamma E. And P2 by P1 is equal to, this will be T3 by T4 is equal to, P2 by P1 is pressure ratio raised to power gamma E minus 1 upon gamma E. This you got, right? From the equation of the first process 1 to 2, you get that from process 1 to 2 you got T2 by T1 is equal to Rp raised to power gamma C minus 1 upon gamma C, right? And if, this is important, if both of them are equal, if in the question both of them are equal, gamma E and gamma C are equal, then from these two equations you can write T3 by T4 is equal to T2 by T1. This is important thing. This is a very, very important relation of the reversed Brayton cycle, and you can directly use this relation for your to solve the question, right? That T3 by T4, the ratio of this T3 by T4 is equal to T2 by T1. This is most important relation, and it will be very useful while solving the numerical, but this is only and only applicable when this gamma E and gamma C are equal. If they are not equal, then you cannot use this formula, right? You cannot use this formula. So this is all about the process 3 to 4, right? That what is the work done, which equations we are using when, and this equation when we are using gamma E and gamma C are equal. Now let us see the process, last process, that is process 4 to 1, right? We already see the process 1 to 2, 2 to 3, 3 to 4. Now the last process which left is process 4 to 1. This process is reversible isobaric heat addition, right? In this heat is adding in the system or in the cycle from the storage device, or you can say from the evaporator. Now if I apply this steady flow energy equation for this process 4 to 1, this will be equal to H4 plus V4 square by 2 plus GZ4 plus heat added to the system is equal to H1 plus V1 square by 2 plus GZ1 plus WCV. And this is a process in the heat exchanger. So in the heat exchanger we can say that there is no work done, so WCV is equal to 0. WCV is 0. So if I assume the first assumption is same, that is changes in kinetic energy is 0 and changes in potential energy is also 0. If I assume this assumption that the changes in kinetic energy and potential energy are 0, so I can write the equation like H4 plus Q. Q is the heat addition, that is QS, heat added to the system, so it is positive, is equal to H1. So QS will be equal to H1 minus H4. QS will be equal to H1 minus H4. So this is used when changes in kinetic energy is 0, changes in potential energy is 0. This is the assumption for using this equation. Now we know that this is a constant pressure process, and for constant pressure process I can write Cp dt is equal to dH for any substance. So no need to take ideal gas again. So I can write Qs will be equal to Cp into T1 minus T4. Cp into T1 minus T4. This equation is used for any substance, whether it will be a real gas or an ideal gas. This equation is used, and same assumption, that is changes in kinetic energy 0, changes in potential energy 0. There is no difference between that. These both equations are one and the same thing because it is a constant pressure process. Now in this equation, this is a constant pressure, so P1 is equal to P4, P1 is equal to P4, right? And also you know that if I write S4 minus S1, this will be equal to Cp ln T4 by T1. From the basic equation of this, ds is equal to dq by T, and in place of dq you can write Cp dt because it is a constant pressure process. So if I integrate it from 4 to 1, this is from 4 to 1, so I can write S4 minus S1 will be equal to Cp ln T4 by T1. So this is the process 4 to 1. So we already covered all this process. What is process 1 to 2, 2 to 3, 3 to 4 and 4 to 1. The basic equations which we have to use in all these 4 processes we already see. Now let us derive for the COP. Now let us derive for the COP. Right, if I rub it, if I apply the first law of thermodynamics for a cycle. Right, you know that what is the first law of thermodynamics for a cycle of a closed loop system or a closed system you can say. So if I apply the first law of thermodynamics, you can feel that if the thermodynamics is a good subject for you, then the RAC is very easy going subject. You can score well in RAC. If I apply the first law of thermodynamics, this is the work done. The work done is WC and WT, work, and heat are QS and QR. So for a cycle, we know that summation of all the heat transfer will be equal to summation of all the work transfer. This is for a cycle and closed system. The assumption of using this is cycle and closed system. This system is closed. We already see that we are considering this complete cycle as a closed system. No mass flow is there. Neither mass is entering nor the mass is leaving. So if I write this equation for this, so we can write what is the net work. Net work will be WC minus WT, WC minus WT will be equal to, or you can write like this if you want to write as per our sign convention, that is WT work done by the system minus WC. Why minus? Because WC is work consumed by the system. So as per our sign convention, this is minus. This will be equal to heat added minus heat rejected. Heat added minus heat rejected. So this is the first law of thermodynamics. This is the first law of thermodynamics for this reversed Brayton cycle. Now if I write what is the COP of this reversed Brayton cycle, we have to find COP of reverse Brayton cycle. Just pay attention here. We have to derive the equation for COP. Now we can write that COP will be equal to, how much is the COP? COP is the refrigerating effect divided by net work. This will be equal to what is the heat supply upon WC minus WT. This is the COP. This COP has no assumption. We are not taking any assumption using this equation. This is a basic equation of COP without any assumption. Using this, you don't need any assumption. For any substance or whether it will be ideal gas or real gas, you can use this. Right? Now, if I write, we know that QS will be equal to Cp into, we already find out Cp into T1 minus T4. If you remember the previous discussion, the assumption of using this is only that changes in kinetic energy 0, changes in potential energy 0. This is the assumption of this. And if you remember that we write work required by the compressor is Cp into T2 minus T1. If you remember this, we solved this. The assumption of using is changes in kinetic energy 0, changes in potential energy 0, and one more assumption is there, ideal gas. You have to use this equation only for ideal gas. And also work done by the turbine will be equal to Cp into T3 minus T4. We already solved this. And assumption of using this is changes in kinetic energy 0, changes in potential energy 0, and ideal gas. You have to use this equation only for an ideal gas. If this is the thing, so I can write from here COP of the reversed Brayton cycle will be equal to heat supply. Heat supply is Cp into T1 minus T4 divided by Cp into Wc, that is T2 minus T1 minus Wt, that is T3 minus T4. Right, T2 minus T1 minus T3 minus T4. If I cancel this Cp, then coefficient of performance will be equal to T1 minus T4 divided by this will be T2 minus T1 minus T3 minus T4. T2 minus T1 divided by T3 minus T4. Just pay attention here. The assumption of using this in the term of temperature is changes in kinetic energy 0, changes in potential energy 0, and ideal gas. This is the point where students are doing mistake, that they are using this equation for the real gas also, but you can't use this equation for the real gas because this Wc and Wt in this form can be only written for the ideal gas, and these two assumptions, changes in kinetic energy and changes in potential energy 0. Right. So this will be equal to, I can write that this is T1 minus T4 divided by T2 minus T1 minus of T3 minus T4. Right. Now let us solve for this. This will be equal to, if I write here, one second, this we can solve it like this. Right. This can be written like, if I write here that this is equal to T1 minus T4 divided by, you can write here, this is T2 minus T3, T2 minus T3, and this is minus T1 plus T4 plus T4 minus T1 plus T4 minus T1. Or you can write, if you take minus here, then minus T4 plus T1, T1 minus T4, right? And if I take T1 minus T4 common, so this will be equal to T1 minus T4 divided by, if I take T1 minus T4 common, T1 minus T4 into, here we have T2 minus T3 divided by T1 minus T4 minus 1. Right, we are solving like this. We can cut these two, T1 minus T4. Right. So from here the COP will be equal to 1 upon this one, T2 minus T3 upon T1 minus T4 minus 1. Right, this is a COP. Now let us say this is your equation number 1. Right, this is your equation number 1. Now if I rub this, Now let us say this is your equation number 1. We know that the pressure ratio will be equal to how much? P2 by P1 or P3 by P4? P2 by P1, this is the pressure ratio, or you can write this is equal to P3 by P4. This is the pressure ratio, we know that. And also we know that T2 by T1, if I write here, T2 by T1 is equal to pressure ratio raised to power gamma C minus 1 upon gamma C. This is T2 by T1, we know that. And for the process 3 to 4, you know that T3 by T4 will be equal to pressure ratio raised to power gamma of expansion minus 1 upon gamma of expansion. Now if we take the assumption that both of them gamma are equal, if I take this assumption, then I can write T2 by T1 is equal to T3 by T4 is equal to Rp raised to power gamma minus 1 upon gamma. Right? So we can write from here, if I take this COP is equal to 1 upon, from this equation we can write COP is equal to, if I take T2 common from this, T2 into 1 minus T3 by T2 divided by, this is T1, if I take T1 common, 1 minus T4 by T1 minus 1. Right? We can write COP, T2 we take common, this is like this. Now, so this will be equal to, if I write, if you solve this, then this is like, if we can say from here, we can say that from this, we can say T3 by T2 is equal to, T3 by T2 is equal to T4 by T1. This is this. If I rearrange this, T3 by T2 is equal to T4 by T1. If I subtract 1 from each side, then again they are equal, right? So T3 by T2 minus 1, or this one, this and this are equal, right? So I can cut this. We can cut this, right? So COP will be equal to 1 upon T2 by T1 minus 1. 1 upon T2 by T1 minus 1. From here we can write COP is equal to 1 upon, what is T2 by T1? Rp raised to power gamma minus 1 upon gamma. Rp raised to power gamma minus 1 upon gamma minus 1. This is the COP of Brayton cycle. You need not to remember this formula, right? If you remember this formula, there are so many formulas in the form of this R raised to power gamma minus 1 upon gamma. If you take complete mechanical engineering, no need to remember this. But again, if you want, then you have to remember the assumptions. The assumption is changes in kinetic energy 0, changes in potential energy 0, ideal gas. These three are the previous assumptions. And one more assumption is this one. That is gamma of compression and expansion are same. These are the four assumptions in which we are using this equation. These are the equations in which we are using this one, right? Okay. So this is the COP of your reversed Brayton cycle, that is 1 upon Rp raised to power gamma minus 1 upon gamma minus 1. So this is the complete derivation of the reversed Brayton cycle COP, various assumptions which you have to take. Don't forget the assumptions. Assumption is the most important part here. right? If a tricky question will come, you will definitely do a mistake if your concepts are not good, right? So this is the COP.